Hi, today we're going to cover resonance forms and curved arrows. Resonance forms are a way of showing how electrons move within a single chemical structure. In order to show how you get from one resonance form to another resonance form, we're going to be using curved arrows. In order to understand curved arrows and resonance forms, you also need a really good understanding of the octet rule. So if you're still a little sketchy on what that is, you might want to pause the video, go back and review that real quick, and then come back to this video. In any event, curved arrows are introduced now when we cover resonance forms, but they're going to be very important later on when we get to reaction mechanisms. So it's great that you're taking the time now to have a deep understanding of how electrons move, whether between two resonance forms, or how electrons can move in a chemical reaction, which is something we're going to be doing a lot of later on in organic chemistry. Okay, so let's go ahead and get started. Okay, so what you're looking at right now is the structure of the acetate anion. So if you look at acetate, you see that there's two forms of it drawn, one form on the left and one form on the right. And if you take some time and carefully examine it, you'll see that the two forms differ only in the placement of the pi electrons and non-bonding electrons. So that's the difference between resonance forms. They differ only in the placement of pi and non-bonding valence electrons. The two forms are distinguished by this double-sided arrow, and that's the way we indicate that these are resonance forms of one another. The reality is actually a hybrid and not one form or another. So in other words, what we're doing is we're drawing these two individual resonance forms to communicate an idea, but in reality, if there was such a thing as a camera that could take a picture of a molecule, it would almost be like the way it looks when you take a picture of somebody kicking a soccer ball and their leg almost looks like a blur. So these electrons are being shared among these three atoms, the oxygen, the carbon, and the other oxygen. And the reality is not one form or another. In order to communicate how we get from one resonance form to another, we use this thing called curved arrows, which is going to be really important all throughout organic chemistry. So curved arrows are used basically to show your logic of how you got from one resonance form to another resonance form. Curved arrows always show the flow of electrons, and they never show atoms moving, only electron flow. And electrons are always going to move from the base of the arrow to the tip of the arrow. So here's that molecule of acetate again, and the only difference between this and 2 slides ago is that now we're showing how we get from one resonance form to the other using curved arrows. So on the left, we're using curved arrows to show how we get to the resonance form on the right. In other words, how did we move the non-bonding and how did we move the pi electrons? If you look at it, what's going on, the non-bonding electrons are moving from the oxygen on the bottom, and they're going to become the pi electrons, and they're going to become a double bond between that carbon and oxygen on the bottom. In order to maintain the octet rule, the 2 pi electrons that are double bonding between the carbon and the top oxygen have to move out and up onto that top oxygen. If you count everything up, you could even pause the video and do this, you'll see that both oxygens and that carbon still maintain 8 electrons total. So they still maintain the octet rule. Remember, resonance forms differ only in the placement of non-bonding and pi electrons. The octet rule still applies, or the form that you've drawn is not valid. Different resonance forms are not always equivalent, and the reality is actually a hybrid. So when you get a question, whether it's in my class or another class, you're often asked on a test or a quiz to draw another resonance form of a particular chemical structure and show how you got between those two forms using curved arrows. So what I'd like you to do is I'd like you to look at this question, and I'd like you to draw another resonance form of this molecule on the right-hand side, and I'd also like for you to show with curved arrows how you got to that new resonance form. So take a moment, pause the video, get out a piece of paper, and see if you can answer that question on your own. And when you've done that, come back to the video and I will go over the answer with you. So here's the answer to this question. So if you look at the left-hand side has the original question that you were given, and the right-hand side is the new resonance form. On the left side, I've drawn with curved arrows how I got from the resonance form on the left to the resonance form on the right. So if we look at what happened, the non-bonding electrons on that carbon on the far right moved, and they now established a pair of pi electrons, which are now the double bond between the two carbons. In order to maintain the octet rule, a pair of pi electrons had to move up and out onto that top oxygen. You'll also notice the charge changes. The charges, if you might want to go back and review formal charges, so it's not the charge that moves, it's the electrons that move, and the actual formal charge on individual atoms changes when the electrons move around. In any event, you can look at the structure on the right and confirm that the new form maintains the octet rule, and that's a great way to check your work and make sure that your new resonance form is a valid structure. So I hope this video was helpful. Please let me know below if I could make any other videos on topics that you would like to see. And I commend you for taking the time to really understand resonance forms and curved arrows. If you can really do this stuff, then you'll be in great shape for most of organic chemistry.